I will share. One sec. Okay, so hi everyone. I'm Raya, and today's class is going to be based on projective geometry, which is like one of my favorite topics and absolutely one of the most fun topics to learn about. So yeah, I hope you enjoy the class. And another thing that I want to say is that it's pretty hard to cover projective in one day. So maybe I or someone else will take another class on it, like in a couple of weeks, but we could just start with it today. So, do any of you have like any idea about projective geometry from like before? Okay, I see in the chat. Like, anyone else? And also, like one more thing, feel free to speak up because it's gonna be hard to see the chat while I go over the theory. And I also would love it if you could switch on your cameras. So yeah. Okay, I see a question. Can we use it in RMO? Fine. Okay, uh, if you've done the RMO geometry problems, then I think it's pretty clear that the problems are very easy by angle chasing and stuff. So I don't think you'll need projective for any RMO probs, but like most people say that it's not very like advised to share, like to, use projective and RMO because like you could get badly graded or unfairly graded. Yeah, it's an overkill. That's what I'm looking for. So yeah, I should start from the basics. And if somebody has any idea from before, I have a buffer problem. So take a screenshot maybe. And if you finish this, you can let me know. Okay. So I
I've
guess
done this problem before in the buffer.
okay, so one sec. Give me a sec. I'll just find a new one for you. This should be nice. Try this one. Yeah, I put it in chat. Okay, a couple of people have seen this prob, but okay, so since we're short on time and have a lot of stuff to cover, I'll just get started. So for projective, oh my God, you've done the G6 as well. Why are you in the class, lol? Because like these probs are very hard already. I don't know where I can find more. Uh, okay, try TSTST 2015 B2. Yeah, okay. So I'll just start with this. So for projective geometry, we are not going to do stuff in the normal Euclidean plane. Instead, we're going to look at the projective plane. So the projective plane is like nothing to be, intimidated by. It's just like the Euclidean plane, but some special stuff goes on here. Like, for example, in the Euclidean plane, we work under the assumption that two parallel lines will never intersect. But in the projective plane, like, we say that if we have two parallel lines L and M, then they will intersect at a point called infinity. So like, and it's not just that, like we all know that parallel lines intersect at infinity, but we are going to strongly use this infinity point in our like computations of cross ratios. So this is like a very prominent thing that's going on. And there is also a notion of direction in here because if you have two parallel lines L and M going in this direction, and you have another two parallel lines, say X and Y, going in a different direction, then the infinity that they're going to meet at is going to be different than this infinity. So Like for notation purposes, we can call this infinity Lm and we can call this infinity xy, but these are going to be different because sort of the orientation is different. So I hope that makes sense. And that is the only thing that you need to know, like at the fundamental point about the projective plane. So let's move on to the more interesting thing, which is like going to take up most of our time today. So that's cross ratios. So cross ratios are a weird thing if you just want to look at them like independently. And it would just seem that they're like weird and out of the blue, but it will all start making sense once we do a few problems. So bear with me. So we define a cross ratio of 4 points, A, B, C, and D, to be AC by CB over AD by BB. Now, this is a weird like definition, but this only works if A, B, C, and D are collinear. So like say you have a line and A, B, C, and D are some points on that line. So this is how we define the cross ratio ABCD. So the best way to remember it, like it's pretty easy once you start doing computations, like it's AC by CB over AD by DB. So yeah, that's how we define cross ratios essentially. So a few properties about cross ratios are, if you look at the cross ratio ABCD, okay, then that is going to be equal to like the inverse of the cross ratio ABDC. And why is this? This is going to be pretty clear because this cross ratio is equal to AD by DB over AC by CB. And AD by DB over AC by CB is precisely what we have as 1 by ABCD. So this is pretty clear, I guess. So also like, so what we did here is we just switched up the C and D. So similarly, we can switch up the A and B also. So this is also going to be equal to like B comma A, like C comma D. And that is also going to be equal to B comma A and D comma C. Because like if you take this one, this expression, and just switch up like C and D here, then it's just going to be the inverse of that. So we can do several switching operations like this, which are going to be pretty useful while we compute. Okay, somebody is asking, why are we defining this ratio? I mean, to ask what is the motivation behind it? Okay, so I just said that like it will feel very demotivated at the beginning, but just bear with me for a second because like this is an amazing technique and it's like very, very useful in solving. So yeah, and let's do a couple more properties, I guess. So the next one is that if like the cross ratio ABCD is 1, can anybody tell me what that means? Like just expand this thing and write it down like I did before. And can you tell me what it means? I highly encourage people to speak up because otherwise it's going to be a monologue.
C and D are the same point.
Yeah, true. So that's correct. But like you can also see that A and B can also be the same point, right? So this implies that A and B are same or C and B are same. Like this implies A equal to B or C equal to D. So if you didn't understand that, what's going on is AC by CB is equal to AD by DB, right? So AC by CB is equal to AD by DB. And you can add 1 to both sides. So that's going to give you AB by CB is equal to AB by DB. So from that, you can get that CB is equal to DB. but like C and D are on the same side of like B, right? So that will imply C equal to D. And this was working under the assumption that A is not equal to B. So if you just work under the assumption that C is not equal to B, C is not equal to D, then you'll get A equals B, like in the same way. Does all of this make sense to everybody? Like, is there any doubt? Again, I would encourage you to speak. Okay, I see the chat. Fine. All right. So let's do a couple more properties about cross ratios. And I would highly recommend to remember these properties because they come up so often while you solve a problem with like cross ratios. You're just gonna regret not trying to remember them. So yeah, I mean, okay, so let's go over them. So the first thing is that these statements are all equivalent to each other. Okay, is there any way I can hide this thing? Because it's just causing me so much trouble. Wait. Okay. So, like equivalent means if any one of them is true, then like all of the others are going to be true. So the best way to show equivalence of statements is that if you want to prove that 1 till 5 are all equivalent, then you can just show that 1 and 2 are equivalent, 1 and 3 are equivalent, 1 and 4 are equivalent, and 1 and 5 are equivalent. Because if you do that, then you can go from 1 to any statement, right? So I'm not going to prove all of these because it's like pretty easy once you have the idea, but I'm just going to give you the idea of how things are going to happen here. So, the first statement is like A, B, C, D are harmonic. And this is another thing that I haven't defined yet, which is if the cross ratio of 4 points A, B, and C, D is -1, then we say that A, B, C, D are harmonic. So yeah, this is the definition of harmonic. All right. So if ABCD are harmonic, then AC, AB, and AD are in harmonic progression. So that kind of sounds convincing, right? Because we're just saying that they are harmonic. So let's try to prove that. So since AB and CD are harmonic, we can say that AC by CB is equal to minus of AD by DB. So you can just take this to the other side and you'll get that AC by CB. I'm sorry for my handwriting. It's pretty bad. Yeah. Plus AD by DB is equal to 0. Yeah. So can anyone tell me how I can get from here to here? Do you have any idea? It's pretty easy, by the way. Just one step of computation. Okay, why is everybody so unnaturally quiet today? What's going on? Fine. Okay, I'll just say it. So just add 2 to both sides. So the way that we're going to do it is like add 1 and 1, and we're just going to add 2 here. So we get like AB by BC plus AB by DB is equal to 2. Do you see it now? I mean, okay, that's not exactly what we want, but okay, I'll just flip it anyway. So, okay, I'm not gonna add 1 to this. Instead, I'm just going to like flip both of these. So what I get is BC by AC is equal to minus BD by AD. So now I can do the operation of like adding 1, like bringing this to this side and adding 1. So what do I get? AB by AC plus AB by AD is 2. Is this clear to everyone? I don't know why you're not speaking up, but is this clear?
Yeah.
Okay. So, and why was I motivated to do this? Could be like a question. So what do we want to prove? We want to prove that AC, AB, and AD are in harmonic progression. So what does that actually mean? So if like the three of them are in harmonic progression, then 1 by AC plus 1 by AD is just equal to 2 by AB, right? So that's why I wanted like 2 to be equal to AB by AC and plus AB by AD. So that's precisely what we have here, right? Just bring the AB to this side and you'll just have 1 by AC plus 1 by AD is 2 by AB. Okay. So therefore we have like reached 2, right? Just 2. So we have proven like 2 from 1. And it's very easy to prove 1 from 2 because all these steps are invertible, right? So yeah, in an essence, we have like proved the equivalence of 1 and 2. And I won't be going over the proofs of the other ones, but I can certainly give you an idea of how you can approach them. And that will be a nice little homework for you to do. There, thing.
By the way, these are all directed signals, right?
Yes, these are directed.
So in
Because
the
like,
fifth point you have made, you have written AN by NB is equal to AC by CV the whole square.
yeah.
Here AN by NB would always be a negative 10th, right?
C by CP whole squared. Okay, yeah, that's true. It's true. Okay, just take mod. I don't care. I only care about the magnitude at this point, but yeah, that's a great point. Yeah. Okay. I mean, or don't even take mod, just say like undirected. And like it is not as like necessary for AN by NB to be negative because
I mean, it's
if
not
my
always negative, but it can be
it can
negative.
be exactly true. So just take it to be undirected. I'm just talking about the length here, just the magnitude of the lengths. Good point, by the way. And okay, how do we prove the other statements? Because like this was just computations without the involvement of the midpoints, but once we involve the midpoints, it's like a bit weird. So the best way to go about it would be to like assign coordinates. And like, trust me, that is very easy because if you just assign the 4 coordinates, then you have m is equal to a plus b by 2 and n is equal to c plus d by 2, right? So you can just do these computations and they are just going to work out. So yeah, I'll just leave that up to you to prove. So like, do you need help with proving these or do you want to try them on your own?
Maybe try them on our own.
Okay, that's great. So, and also I would just recommend to remember these because like, okay, maybe not the statement 2 because like that does not come up very often, but 3, 4, and 5 are like very common if you're doing like serious cross ratio chase problems. So maybe just remember them. Yeah. Fine. So the next thing I want to talk about is like, okay, we're doing projective geometry, but we are not projecting anything. So let's start projecting once we have the definition of like cross ratios. So the first definition here, okay, I don't like definitions, but like I'm saying that these are definitions, but they in essence are not. So if you have like 4 lines like these, which are like concurrent and stuff, okay, this is a bad diagram actually. If you have 4 lines like these, then like we call these collection to be like a pencil. And it does not necessarily have to be 4 lines. It can be any number of lines, but they have to concur at a point. So we call that a pencil of lines. And like the best thing about pencils is that we can project cross ratios in a pencil. So like, let's see how that happens. So right here, I have a pencil of L1, L2, L3, and L4. Okay, somebody is asking, we call those lines as pencils. Yeah, I mean, pencil is just a collective noun for lines. I mean, doesn't matter, right, what we name them. So yeah. So these are pencils. And if you take a transversal, say x1, and you get the points like, okay, this is x1 and this is x, say. So if you take two transversals and you take the cross ratio of the intersections of x with all the lines, so what will the cross ratio be like? This cross ratio will be A, B, C, D. And the other cross ratio is going to be like A prime, the same thing with primes. A prime, B prime, C prime, and D prime. And the best thing about pencils is that these two cross ratios are going to be equal. So like if you have a harmonic pencil like this, like I'm saying harmonic pencils, but doesn't have to be harmonic because it can just literally be anything. So if you have a pencil like that, and you take any random line across the pencil, and you take the four intersection points, then the cross ratio is always going to be preserved. Like ABCD is going to be equal to the cross ratio of these 4 points. But like you have to preserve the order. You just can't say that ABCD is equal to A prime, C prime, B prime, D prime. You have to like preserve the order or like in one way or another. So that's like the thing that's going on. Right. So that's projections. And like there's like a trig version of projections, but I don't think we should do that right now. Okay, let's just move on to some configurations because those are fun. So the first config that I want to talk about is like, okay, like somebody asked at the very beginning, what is the motivation of defining like cross ratios like this? And I think that's the whole point of projective geometry. Like that question is the most prevalent. So this is probably going to solve some of that confusion. So if you have a triangle ABC and you have the midpoint of a side BC, okay, I have like a question in the chat. Is proving the fact that the common ratios are equal basic for those pencil? Okay, wait. So to prove that fact that the common ratios are equal, like you just need nothing but like a bunch of sine rule spam going on because just compute these ratios in terms of sines of these angles and like these sides like PB, PC, PA, PD. And like just take the sines of those angles and sort of prove it for this. So like the proof is not necessary as long as you remember it, but if you're doing it for the first time, then I would advise like you to prove it. So yeah. So the first config that we have is if ABC is like a triangle and M is the midpoint of BC, and you take like a line through A parallel to BC, then like, and you like, okay, at first we define that two parallel lines intersect. So this line and BC are going to intersect at infinity, but the direction of that infinity is the same as the direction of BC. So we just call that infinity BC. So the claim that I'm making here is like the points A, B, M, and infinity BC are harmonic. So can any of you tell me a quick proof for this? This is like very easy.
Isn't it BCM and infinity?
Sorry. Okay, I'm sorry. Wow, was that type? Thanks for that. Yeah, BCM and infinity. Harmonic. So can you tell me a quick proof for that?
We can just write it out like we write out the cross ratios, and like we can think of infinity like we think of it in limits.
True. So, well, so the cross ratio is going to be equal to Bm by Mc over B infinity by infinity C. And like Bm and Mc are equal, right? So that is just equal to 1. And b infinity by infinity c. So like that's something like b till infinity. I'll just do it, right? B infinity by infinity c, right? And since I'm taking the point at infinity, those lengths are not really relevant here. So we can just assume that b infinity and infinity c are equal because this is a finite length, no matter how large it is. So that is also equal to 1. But like there's this thing that you should look out for, which is in order for them to be harmonic, you just can't say that that is like equal to 1, because if it was equal to 1, then either b would have to be equal to c or m would have to be equal to infinity. But that's not the case, right? So like we always say that this is equal to -1. And okay, in essence, like when is it equal to -1 and when is it equal to 1? So if both of the points m and infinity are in between BC or like farther away from B and C, then it is going to be 1. Like then it has a possibility of being 1. But if you have BC like this, and one of the points is inside the segment BC, and the other point is like outside the segment BC, then it is always going to be negative. So that is how we define the cross ratio, right? Does that make sense?
Yeah.
Okay. All right, so that is a configuration that is like a very basic one, and you should obviously keep in mind. So whenever you see like a triangle, you have a midpoint and you want to prove something parallel to something, or like you just want to prove midpoint, just say for like for the sake of it, and you have a line parallel to the base through the topmost vertex, then just take the midpoint and try to prove that this cross ratio is going to be -1. Then you'll just be done. So that is like a useful trick to do. So yeah. So the second config that we have is like Keva Menelaus, and it is called that because like you see both of Keva and Menelaus going on here, right? Because if you take ABC as the triangle and ADBECF as the Sevians, that's Keva for you. And if you just take EF to be like a transversal and like that intersects BC at H, then that's Menelaus for you. Like the yellow part is Keva and the pink part is Menelaus, right? It just looks like Keva and Menelaus all combined in like one thing. So yeah, so what is the statement of this first of all?
H comma D and B comma C is equal to -1.
Exactly, perfect. So okay, I'll just write it flipped, but that does not matter. So B comma C, D comma H is minus. Yeah. All right. So how would we go about proving this? Do any of you have any idea? Because I'm just going to give you the
We can
idea.
just use Menelaus and Kiva theorem.
Yeah, we can just spam Menelaus, right?
Yeah.
Kiva like a lot of times. And we'll just arrive at this because what do we need in essence? We need BD by DC like over BH by HC to be -1. So what are the ratios we need? BD by DC, BH by HC. So BD by DC we can of course get by Keva in ABC, and BH by HC is like obviously Menelaus, because what is the statement of Menelaus? It is like CH by HB times BA by, okay, no, what am I flipping? Yeah, I am flipping, yes. So HC by CB times BF by FA times AE by EC, all directed, is equal to -1. That's Menelaus for you. So like if you know the ratios BF by FA and times AE by EC, which you know by Keva, you can just say that like CH by HB is something that's related to those two ratios. And also like by only Keva, you can just say that BD by DC is a ratio in terms of those, because Keva says that BD by DC into CE by EA into AF by FB is like 1 if you take the directed lengths. So you can just spam Keva and Menelaus and do that. So like, do I have to prove it or do you want to do it?
No, it's fine.
Okay, all right. So let's move on to the third config. And this config actually has two parts in it. So the first part is like okay, the config is called angle bisector theorem, but it's not the angle bisector theorem that you think I'm talking about. But anyway, okay, what's going on? Yes, this should be fine. I'm not sure a straight line using this tool. Yeah. Okay. So if you have a triangle ABC and you have both the internal and external angle bisectors, and let's just say that the internal angle bisector of angle A intersects BC at D and the external one intersects BC at like D prime, then the thing you can say is that BCDD prime is -1. Okay, that is a weird diagram because we should have not done that. Oh, let us choose to. Yeah, it's going to look something like this, and there has to be a 90-degree going on here, but I'm just not going to go into details. So, like, let's say ABC is our required triangle, and AD is the internal angle bisector, and AD prime is the external angle bisector. So what's going on here is BCDD prime is -1. So can you prove that actually? And that is very easy, to be honest. It's just very trivial.
Draw a line from D that is parallel to AD dash.
Mhm,
So let's say it meets AC in, let's say, X,
mhm,
and it meets AB in, let's say, Y.
mhm,
So we're gonna get that CDX is 90 degrees.
mhm.
Yeah, and
Wait,
the
no,
rest
not
is
CDX, right?
no,
CDX
I
is.
meant ADX. I meant ADX. My
Yeah,
bad.
sure, sure. ADX is 90, yes.
And yeah, the rest is just finding similar triangles and like sine rule chasing and all.
Exactly, yes. Or like, okay, that's a bit complicated, but you can also say it like in terms of internal and external angle. Somebody says sine rule. So yeah, sine rule works perfectly because if you take this to be x, then this is 90 minus x, and this is 90 minus x, and you can just make sine rule work. But like the best way to do this is like we want BD by DC. Okay, I'm not sure if this works, but I can just try. BD by DC over BD1 by D1C is what we want, yeah? So see, since AD is the internal bisector, then BD by DC is equal to AB by AC. So we can just rewrite AB by AC. And BD1 by D1C is also AB by AC, right? Because it's like external angle bisector theorem. Like BD prime by D prime C is going to be AB by AC. That's just external angle bisector theorem. If you remember, like, yeah, does that make sense?
Yeah.
Okay. And like it's in essence, it's minus AB by AC because the directions are opposite. So like it's going to be -1. So that's how you arrive at it. And the similarity thing that someone said is like exactly the way to get to this from scratch, like the way to get to the angle bisector theorem from scratch. So I'll just write spam angle bisector theorem. And also like another thing I did not prove, it's like spam giver and analyze. Yeah. So like also like doing trigonometry from scratch for here would just be another way of getting to the angle bisector theorem, which is pretty redundant if you know angle bisector theorem, but it's fine if you want to do it that way. So yeah, this was part one of the configuration, and part two is a bit different and sometimes even more useful than part one because part one hardly ever comes up. So uh, fine. Okay, this is hard to draw actually. Yeah, I'll just draw a triangle real quick. So A, B. Okay, I have written the statement in a weird way because I was talking about the lines, but I'll just rephrase it. So just ignore this for a while. So what I'm trying to say is like, okay, this was for a different configuration overall, so I'll just state it anyway. So if BCDD prime is -1 and the angle between AD and AD prime is 90 degrees, then like AD and AD prime are the internal and external bisectors of like angle BAC. So I'll just state that once real quick. So if BC D prime is -1 and angle DAD prime is 90, then AD and AD prime are the internal. And can any of you prove this? Like or any idea on how to prove this?
I mean, the above theorem, if we're given like any two conditions, then the third condition is like trivially correct.
Exactly. So yeah, that's essentially the idea. Or you can just rephrase it like if you have one of them to be like the one of the angle bisectors, then it's like the other one is always going to be the angle bisector. And like,
Yeah.
yeah, it's just that. So does that make sense to everyone? Or should I go with the proof? Or do you want to do it on your own?
Yeah, we can do it on our own.
Okay. Also, like, why is only one person speaking up? What's up, people? Like, yeah. Okay, sure. All right. So we will define cross ratios for concyclic points now because we were just doing it for linear things going on. And therefore, the next thing that we want to do is cross ratios for like cyclic points. So if you have the points A, B, C, D on a circle and you want to look at the cross ratio A, B, C, D, and like let's say you have a circle. Can I draw a circle from here? Oh my god, that's sad. Okay, I'll just have to draw it by hand then. So if like this is a circle and like A, B, C, D are 4 points, just let me draw them randomly. B, C, D. Then if you want to look at the cross ratio, then that is just equal to like, just take any point P on the circle. P is like a random point on the circle. Like let's call the circle omega or something. So if you pick a random point P on the circle, then this is just equal to the ratio PA. Like this is just equal to the cross ratio actually, PA, PB, PC, and PD. Okay, does that make sense?
Yeah.
Okay, so like there's also a trigonometric way that you can say this, like in terms of the angles between the lines PA, PB, PC, PD. So, okay. And like sort of the thing that's going on is since you can take P to be arbitrary, like this cross ratio is like going to be independent of P. Like no matter whatever P you choose, then like it's going to be independent. And if you like take the signs of the angles, like angle APB, BPC, CPD, and like all the other angles that are going on here, you can also like be able to say that this cross ratio is equal to like, mm, wait, okay, can I say that? Okay, no, it doesn't matter, right? So the claim that I'm making is since P is any point, the cross ratio is independent of P. And that makes sense actually, right? Because just take a point Q here and the cross ratio will be totally like different according to the claim that you have made. So does that make sense actually? That it will be independent of Q and P, like, or whatever point we are taking it from, like whatever perspectivity we're looking at from. Is that clear? Oh, okay.
Some guy in the chat asked something.
Let me see. Sorry, but what the cross ratios for the lengths mean? We have only defined cross ratios for, yeah, okay. So this is a valid question actually. So like, this is like not exactly a cross ratio. When you have like names of lines going on in here, that means you're just going to use it for perspectivity. Because like, this is not cross ratios of the lines, because if you had the ratio ABCD, then you could just say AC by CB, AD by DB. But this is like a notation thingy, which implies that you can take any point P, join these lines, and take another transversal to it, like, and then like take the intersections with PA, PB, PC, and PD. So whatever points you get, like X, Y, Z, W, then it is going to be like the cross ratio of X, Y, Z, comma W. So that is why we say like it is equal to PA, PB, PC, PD, but it's more like a notation thing. Just it
Yeah.
doesn't mean that we are taking the ratio of the lines or something like that.
We
So
Does
can
basically, we're
take
looking
any.
at.
yes, go on, someone.
So basically, like we're thinking of them as rays.
Exactly, yes. And like this is just the projectivity that's going on, like the one we talked about before. So we just write it as PRBBCPT to be able to like project it onto other clients. And by clients, I don't just mean circle like lines, because I can also project it onto another circle. So if I like have a bigger circle here, I can project it onto like from the line, I can project it onto the bigger circle. So that is like another important thing. Okay. So Ronak, you were asking something, right?
Yes, I am wondering that the line is random. I mean, for PA.
Transversal?
Yes.
Okay, so it is random because like it doesn't really matter what transversal you take. Because like if you
Okay,
take
okay.
this transversal, then like it's going to be the same for any other transversal. That's what we did here, right? Yeah. So take any transversal, doesn't really matter. But in essence, the cross ratio of the cyclic points like ABCD is always going to be equal to the one we said before, which is like AC by CB, like over AD by DB. But like we are taking the transversal to be able to see it in terms of perspectivity. And this PAPB is only like a notation thingy that's going on. Yeah. I should have
Okay.
clarified it. So good point.
Here,
All right. So
I'm just having one question.
sure,
Here,
go on.
this is the cross ratio is independent of B because of the angles being equal in the circle, right? In
Yes,
this.
exactly.
So,
Like subtended by the arcs. Yeah.
yeah. So circle is special in this case. Is this also true for any other shapes?
Well, not really, right? Because like it's not going to be true for other shapes because like if you have any other conic, then you can't say that the angles are equal. But like if you define the cross ratio for a conic, like let's say you have another conic and you define the cross ratio, then like you can take perspectivity as well. Because if you take a line, like a transversal line, like the one we have here, you can still define the perspectivity. Say like you have an ellipse and you have 4 points A, B, C, and D. Like you can still define the cross ratio for A, B, C, and D to be like AC by CB, AD by DB. And like if you take a point P outside or on the conic, and you can like, and you take another line, then you can certainly project these ratios onto the line. So
But
like,
this will matter on the position of point B, right?
exactly. So that will be dependent on P. So like circle is a nice thing that happens because of the arc angles.
Okay.
Yeah. So, yeah. And like, okay, I know I'm throwing a lot of theory at you without like doing any problems, but I promise that this is going to be the last bit of theory that we're doing, and then we'll just get into some nice problems. And do I have anything in the chat? Can you explain perspectivity again? Okay. Yes. Perspectivity is like very important to understand because it's one of the main things that's going on in projective. So yes. So what is perspectivity? Like this is perspectivity at its like very basics. So there is another layer of perspectivity, which is not this, but I'll just go over it again. So if you have a pencil of lines like 1, 2, 3, and 4, and you take a transversal through it, then like the cross ratio of the 4 points that the transversal intersects the line at, like let's say that those 4 points are A, B, C, and D in that order. So like that cross ratio is going to be equal to, like if you take any transversal and you call these points A prime, B prime, C prime, D prime, then that cross ratio is going to be equal to A prime, B prime, C, D prime. So that is what perspectivity is. And why do we call it perspectivity or projective? So like in essence, like take this common intersection point of the lines P. So like in a way, we are taking a transversal and sort of like interpreting the angle between the lines in the transversal. Because if you just have a line and you have like 4 points on it, and you have like something like this, then what essentially are we doing? We are just fixing these angles, right? So quintessentially, if we have 4 lines and we take a transversal, the only thing that we do by taking that transversal is fix these angles. Because if you take another transversal, those angles are still going to be fixed. And cross ratios are 100% dependent on angles. So essentially what's going on is whatever transversal you take, you never change the orientations of these lines, right? But these 4 lines are fixed. So this can't come closer to this or something like that. The angles are always fixed. So that is why like the cross ratios just remain constant no matter whatever transversal you take. So that is essentially perspectivity. Does that make sense? Okay. And another thing about perspectivity to make it more intuitive is like the trick version I skipped. So I'll just go over it. I actually don't want to throw a lot of theory at you but anyway, let's just make it clear and not skip it. So if you have 4 lines like A, B, C, and D, I'll just draw the same diagram over and over again. Wait, I could copy paste it. Could I copy paste? No, let's just that. So if you have 4 lines, A, B, C, D, and if you like take a transversal through them and call it L, then I'm claiming that like, okay, let's call these P, A, B, C, and D. So like someone just said that we can't take cross ratios of lines, right? And then I said that we are looking at points instead of lines. So if we take the cross ratio like A, B, C, D, we in essence denote it to be the cross ratio of the 4 lines A, B, C, and D. So what exactly is going on? Like if you have 4 lines like this, and you are asked the cross ratio of that, so it's going to be hard, right? Because you just can't find the ratios between lines. So what you're going to do is take a transversal, take the 4 points, and take the cross ratio. So that's essentially what you're going to do. And that is how like, that is another like dimension of perspectivity that's going on. So what I want to define is like the cross ratio of the 4 lines A, B, C, D is a cross ratio of the 4 points of intersection of like a transversal with the lines A, B, and C, and D. And this is equal to sine of the angle between A and C over sine of the angle between C and B, whole thing over, wait, okay, can I scroll? Sine of the angle between A and D over sine of the angle between B and D. And this is actually very easy to remember because if you had cross ratios, what would you do? You'd do AC by CB over AD by DB. So that's essentially what we're doing, right? So this is AC by CB and AD by DB. Just made it invisible. But, so this is the trig form. And this is going to make it more intuitive because like, see, the angles between AC, BC, AD, and BD are always fixed, no matter whatever transversal we take. So like the cross ratios are always going to be fixed. So that is essentially why the cross ratios remain fixed, even if we like shift up the transversal to something like this or something like this. So does this make sense? And like for the proof of it, I'll just send you a note of mine. Like I'll just write down the proof, LaTeX it and send you or something like that. But like for the proof, like it would be best if you try to do it yourself. And the only thing you can do here is just spam sine. I mean, I can't even begin to tell you how much pain it is, but if you really want to do it, then it's fine. You can just spam sine rule to like these triangles, PAB, PBC, PCD, PDA, and just get stuff in terms of angles between these lines. So is that clear to everyone? Anybody have any questions?
Yeah.
Okay, cool. So yeah, last bit of theory that I'm going to throw at you is like some properties about harmonic quadrilaterals. So we define cross ratios of cyclic quadrilaterals. So does anybody have any questions about cross ratios in cyclic quadrilaterals to you? Or is that clear to everyone? Because like it's going to be the most important thing in projective geometry we do like at all. So is it clear to everyone? Only then I can move on to the
Yeah.
next part. And I need at least 4 or 5 responses because like this is weird. So nobody's
So given a cyclic code, how are you exactly taking the direction of the points in the sense?
okay, so okay, direction, right. So this is a weird thing that we do, but trust me, you're never going to use direction for cyclic quadrilaterals and cross ratios. So if you have 4 points A, B, C, and D, then like the cross ratio AC, BD is going to be negative. But AB this is a terrible lag. This is positive. So in essence, like for straight lines, what we did is that if we had both the points lying between A and like B, then the like either both in between A and B, like C and D are both in between A and B or both away from A and B, like not in the segment, then the cross ratio was positive. But if one is inside and one is outside, then the cross ratio was negative. So that is exactly what's happening here. Because if you take A and C and you take one of B to be in between A and C and one of D to be on the other arc AC, then that cross ratio is negative. But if you take it like both on to be the same arc, like for example, if you're taking AB, then C and D are on the same arc AB, like the major arc AB in this case, then the cross ratio is positive. So that is how we define direction. So yeah, does that make sense?
Yeah.
Okay, what? There's a question on the chat. Is there no kind of config problem here ever? Are we using normal vanilla angle between two lines or should we use direct angles? No, it's just normal angles, like no directed angles going on. And like, of course, like there's a lot of config geo you can do because like, have any of you ever done chapter 4 of EGMO? Like, have any of
Yeah.
you ever? Okay, like that has a lot of like terrible config props. And like the first thing I ever did was like learn projective. After I learned angle chasing and POP, I didn't even learn config geo. So Dude, I'm not ours at Geo. So tell me how you saw ours at Combi. Lol. Okay, anyway. So the only thing I did after doing POP and angle chase for a long time is like projective and inverse. So I literally, solved all the problems from chapter 4 of EGMO, like almost all, like 90% of the problems on like, yeah, just using just projective geo. And like everybody just banned me for that, but I don't know, that was much more intuitive than like, okay, the chat is getting a bit weird, so I don't know. Maybe, yeah, should be a bit decent. Yeah. Anyway, so yeah, the config geo is like trash according to me, and projective geo is the most powerful. So yeah.
Combi as a whole
All
is
right.
trash.
Haha.
Combi as a whole is trash.
Okay, I can't agree. Yes, no, Athar, I can't ban him, but Combi is not trash. If you think Combi is trash, then what is algebra? I don't know. I can't even start talking about that. So yeah. Oh my God. Okay, no more discussions about what is trash and what is not. So yeah. Anyway, let's move on with the last bit of theory that we want to do. So is the direction thingy clear? I don't know. So the one who asked me this, like when it is positive, when it is
Yeah, it
negative.
is
It's
clear.
clear?
Yeah.
All right. So just, hey guys, stop it in the chat. Like, yeah. Anyway. So let's move on to the last bit of thing that we are doing, the theory. So this is like harmonic quadrilaterals. And this is the most interesting thing among everything we've done till now. Why is it so small? Yep. So I'm going to define harmonic quadrilaterals such that if you have a circle A, like so a cyclic quadrilateral ABCD, and you take the circle through them, then ABCD is harmonic if AC BD is -1. And this uses the config fact that I told you a second ago, which is like if both of them are on the opposite arcs, then it is negative. So let me draw something. Tangent and a second. Yeah. So this is a classic example, and this is like the only example of a harmonic quadrilateral. So I'll get into more depth about why this is the way I drew it. Any questions in the chat? Oh, it's been 20 minutes since last bit of theory, but I promise I'll be done by 5:45 something. Then probs. Because like projective geometry has so much theory, and I was talking about it with Shreya, and she was like, we need so many classes for projective, and I was like, true. So okay. So I'll write a few statements for you, and we would try to prove that these are like equivalent conditions for harmonic quadrilateral. So the first one is ABCD harmonic, of course. And the second one is like undirected. I'll just put it in bracket. AB by BC. Wait, what? No. Oh. Just let's skip this, right? Oh, true. Yeah, so the third one is, second one is tangents. Right. And if at any point my handwriting is illegible, just let me know. Intersect at and tangents at B and D intersect. Okay, not at exactly, on, I guess. On AC. Okay, so this is like absolutely the most powerful thing that's going on. So if you have any like harmonic cyclic quadrilateral, like A, B, C, D, then the thing that this says is that the tangents at A and C are going to intersect on the line BD, and the tangents at B and D are going to intersect on the line AC. Trouble? Mhm. So this is what a harmonic quadrilateral should look like. Yeah. So I'm not going to get into the proof of this because like it's going to be bad.
It's just medians.
Yes, it is a medians, and it has like a cross ratio chase proof as
Yeah,
well.
we have to use perspectivity once.
Sure. Yes. Okay, somebody asked DDIT class when? Lol. Okay, so we didn't even have DDIT in Sophie, but yeah, so it's gonna be late because you don't need DDIT for at least in most. You need it for TSTs, but not for in most. Chill. Oh yeah, DDIT is like Desargues dual involution theorem. That's like one of the last theorems, last bits of theory you need to do for projective. So yeah, don't worry about it. Fine. So like you can try to prove this on your own and I'll leave it as an exercise. And also I'll include it in my problem set. What is going on? Okay, if you have anything like legitimate to ask me, just unmute, okay? Because reading the chat is like distracting me so much. Okay. So yeah, fine. So I will not do the proof. I'll just leave it up to you and I'll also include it in my problem set. And if you at any point can't do the proof of this, you can just consult EGMO or like any other handout because like most of them will contain this anyway. So yeah, this is the thing that I wanted to talk about in like harmonic quadrilaterals. So I guess we could just move on to a couple of problems. Would you guys like that? Or do you?
Yes, yes, please.
Haha, okay, sure. Give me a second. I'll paste the prop. Wait, wow. Just a second. Which one did I want to do actually? That'd be nice. Oh, what if I don't find the problem set? Okay, one sec. I'll just write down the first problem and I try to find the second one. I don't find it. Okay. So this is like a Sharigan problem. I don't know the year. It's from the book. So ABC is a triangle where BD is the altitude. So construct the circle with BD diameter. Let it intersect AB and AC at A and L. The lines tangent to the circle at K and L intersect at M. Prove. And if you know this problem, then please don't spoil it because like there are a lot of people who have no idea about projective geometry and I got a lot of DMs before class talking about
Okay, sure.
trying to do. You have done EGMO chapter 2 and chapter 3 a bit. Have you done chapter 1? Okay, you have done chapter 1. So for me personally, after chapter like 1, 2, and 3, I was forced to do chapter 5, which is like computational, but yeah, it's just not good. So I would recommend you can either, if you do want to learn bashing, which is tragic, by the way. So if you do want to learn bashing, then you could just do chapter 6. But if you don't want to learn bashing, then you could just move on to inversion, because if you come back to config geo after learning inversion and projective, that's going to be so much easier. That's probably the best decision I've. So why tragic? Because bashing is bad, and I hate bashing. Yeah. Okay, so to the people who have not solved the problem, try to do the problem.
Are you sure it intersects AC? Because I think AC will be tangent, no?
Sorry, what? No, it is going to bisect AC. Yeah, AC is going to be tangent to the circle, yes, but BM is going to bisect.
No, like in the problem statements that let the circle with diameter BD intersect AC at L. AC, I mean, yeah.
Oh shit.
I think it should be
Okay,
a
BC,
BC.
BC, 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 yeah.
Yeah.
Sorry. I'm trying to find the handout desperately, but I just don't get it. Yeah, got the handout, yes. So oh, actually it was like written wrongly in the handout itself. Wait. Just paste it. Yeah, but there has to be an edit. Just like it will be BC, like over this. Yeah, should be good. And this will be BC now. So do any of you have any idea about how to approach this? I mean, synthetic solutions are also encouraged because it's your first time doing projective, but yeah, I would prefer a projective one. So let me just draw the diagram. Yes. So ABC is a triangle. And to the people who have already done projective, these problems are very basic because like you should start at the basics because projective geometry is pretty confusing. So if you don't feel like doing these, you can always go back to the buffer problem I said before class. And have any of you, if any of you have any progress on the buffer problem or you have solved it, then just tell me. I'll just find another one for you. This is some circle which looks very weird. It'll, yeah. So this is K and this is L and this is D, I guess, right? Yeah.
The altitude is BD.
Oh, okay. I have to, is it? Yeah. B. Okay. This should work. And like I'll take the tangent intersection at K and L, right? Color. Yeah. Okay, also never draw diagrams like me because like you should always try to do freehand diagrams and not use scale to make ones that look particularly nice. You have done?
Yes.
Okay, how did you do it? Yeah.
I found by angle chasing that BKL is similar to BCA.
DKL is similar to BCA. True, that will happen, yes.
Then BM is Semitian of BKL.
Yes,
And
true,
by
true.
B.
Yeah. Okay, so this is solution one. Like, this is synthetic, by the way, and like
If
BM.
BM intersects the circle BKLD at X,
Mm-hmm. Yeah,
then we know that BKXL is harmonic.
true,
So we can project the bundle from B and
true,
know that the B tangent is parallel to AC.
true.
So we get AC, the intersection point of BM and AC, and the point at infinity is a harmonic bundle. So
True.
E is the midpoint.
Perfect. Okay. Yeah, that's exactly what I wanted the solution to be. So this is the synthetic solution. Okay. So the solution that I intended is like, first of all, since M is the intersection of tangents at L and K, and like MB is a secant of the circle, do you agree that B, X, L, and K is harmonic? And I want everybody to like speak up because like this is really important.
Yes, they are harmonic.
Yes, okay. So this is like -1. And so you can just project this bundle from B, right? So take it from B. So you can just say that, yeah, BB, which is like the tangent at B, comma BX, BL, BK is -1. Yeah. And from that, you can just project it onto the line AC as transversal. So like, what are we taking? We are taking perspectivity from B, and then we are projecting onto AC. So like, let's say that this is E, like Atharva said. So like, and also BD is like the diameter of the circle. So the tangent at B is going to be parallel to like the perpendicular to the diameter. So it's going to be perpendicular to BD, and BD itself is perpendicular to AC. So this thing is going to be parallel to AC, right? So then we are going to get infinity AC and then like BX. So what is BX? BX meets AC at E. So this is E. And BL is like C. BL meets it at C. And BK meets it at A. So this is -1. But see, like, so from this, we know that this is a harmonic bundle. But E, like, has to be the midpoint, therefore, because we did in the config.
The converse.
Yeah, exactly. The first config, right? So if like the infinity in this direction is like harmonic conjugate of some point, then that point has to be the midpoint. So here, like infinity AC is the harmonic conjugate of E. So the like E has to be the midpoint, right? So that will help us conclude that E is. So is everybody clear with this? Like this should not be very hard because like it's a basic ones. Bro, Om is here. Okay, hi Om. Okay. True. Okay, so you didn't see it at once, and that's completely fine because like it'll take some time to get the hang of because like it's new to you, right? So don't worry about it too much. You'll get it, no problem. So let me give you another problem to do. Okay, maybe 2.2. Yeah, it should be nice. Like today's problems are going to be very easy, and Arnav, I guess, is going to take a PSS after I finish all of the theory, so you'll have nice problems there. But it's really important that you get these easy ones, real solid. So try this problem. What? Why do you want to bash it? Like, this is the last sort of thing you should bash. Like, it is so nice, actually, like synthetically, even. I mean, if you don't even think about projective, and I just said that I hate config zero, but if you try to think about it in terms of config, that is going to be like a lot better. Why do you even want to bash it? I don't know. Just draw the diagram once properly and you'll see how good it is. My God. Okay, like my policy is art school policy that is like don't bash for at least the first 20 minutes of trying the problem. So yeah. Was it 20 or more? Yeah, something like that. And also I was talking about drawing the diagrams like by hand and not to use like scale and compass and that sort of thing because like that is actually a very bad thing to do and I've gotten into such a weird habit of doing it that I can't get out. So I just don't want you guys to develop that habit. Try to hand draw. Yeah, so this is, oh no, this is not B. This is also, yeah, this is not A, this is also B, right? Yeah, internal, external bisectors of angle B. I hate when triangles are like built on the base AC because that's just so weird. So this is external bisector, right? So like, let's say that this intersects at X prime and this does it at X. So, sure. And like, this is the orthocenter, like, let's just say, I'll take the altitude, so it's better. And the altitude, something like this. Yeah, this is H. Wow, what's up? One sec, my laptop is out of charge. Just be right back. Yes, I am back. So what was the question? The projections onto the internal and external bisectors. So I always thought what's going Yes, compass should work here. And what do you mean art school is obvious?
For me, it felt like it was obvious that you should try it in the beginning with like a freehand drawn diagram.
Yeah, like I
But
don't.
why? I mean,
Ruler and compass seems like
when
extra effort.
No, because
like when I did art school for the first time, I just did ruler and compass for all of the problems, and I disregarded even. So why?
like the point is that firstly, it's a point of energy. Like I am too lazy to draw it properly. Secondly, like
Uh-huh.
when it's too perfect, I feel like it's stuffy. Like I don't solve. I solve better in a free diagram with more sloppy
Okay.
stuff.
When
Okay,
you
but
can
don't
draw
you see
the.
like many claims with perfectly drawn diagrams?
No, I don't.
You don't. You don't. How do you see claims in those?
I
Like
see it. I see it.
something looks cyclic, right? Something looks parallel, something looks midpoint, something looks cyclic. That
That looks
that
even
doesn't
in
happen?
freehand though. If you draw it well enough in freehand, also it looks like that.
Yeah, so like I can draw a straight line very well in free line. After some practice, I can draw circles. So like drawing in compass, so if it's a very clustered diagram, I draw the basis of it in like a pencil and compass.
Uh-huh.
But then after that, I just do freehand. Like,
Okay, okay. Yeah,
but for problems like these, I always use freehand.
sure. Okay. Like if I do freehand, I wouldn't even be able to tell if like AD was perpendicular to VC, so it's better for me, but yeah, try. Okay, lol, no more discussion about trying. So anybody, any hints, like any clue about how to do this projectively? Like because this is very easy, right? I mean, what's
The
going
angle
on?
bisector thing.
How would
Because
you use it?
because we have like perpendicular lines and stuff, and we have the angle bisectors.
That is true, but how would you want to use it? I don't know. Do you have a concrete thing going on? Okay, I'll just give you a hint, like just
No,
a
because
tiny.
like angle NBM is actually 90 degrees.
Yeah, yeah.
And because the ABX is equal to XBC.
Wait, we can just project out of the
ABXH.
circle, right? BH.
That's what
Circle
I'm trying to
with
say. Now there's a
circle
circle,
with
but
diameter
nobody
BH.
identified it, right?
Just project onto that,
Yeah, true, very true.
and
So, like,
something will work.
do you people see that there's a circle here? Like,
Oh, and then we can just do the EF tangent.
exactly, exactly,
Yeah, we project through
exactly.
B and something
F
something
and B, the
also.
tangents meet at M.
Huh, exactly. Why do you not see that there's a circle?
It's
Like, what?
actually so smart.
I
Right,
find
yeah,
it a
tangent meter. Oh,
question.
that's nice. That works.
Yeah, this is a circle, right? Because just all the angles subtended on BH are 90. Like, the
It's
diameter
not,
is BH.
it's not that obvious that there is the circle.
You can see 90 degrees from them.
Like we've not drawn the diagram. So if we draw it, it would probably be visible for us.
True, true, true. That's why I'm saying not draw the diagram. Yes. Anyway. So, like, okay, there's a circle, but what after that? Like, somebody who does not know projective, do you want to take a try on what could be happening? Like, there's a circle that passes through like BNFHMD. BNFHMD cyclic. Yeah. That's the first thing that's going on. Okay, so what can we say about that? Are there any people talk?
I mean, if you show that the quadrilateral NFMD is harmonic, then you're done, right?
Yes, true. And that is actually okay. So that is a great intuition because like we eventually want to show that NFMD is harmonic, which is precisely what you said. So in order to prove that, oh God, what harmonic? Okay, yeah, harmonic. So in order to prove that, like just take it, like assume that it is harmonic, then what else is true? So if you take like X prime C or like AC to be the transversal, and if NHMD is harmonic, then what is true? You see what I'm saying?
XA, X dash A, XC harmonic.
Exactly.
Perspectivity
Okay, you
from
messed
B.
up the order, but
Yeah,
fine.
okay.
Always follow the order because that's gonna cost you
Yeah,
your entire marks. Yes. So this is harmonic is essentially what we want to prove, right? And this is true by our angle bisector thing, right?
yeah.
Okay. So if we have that this is harmonic, like okay, now we are going in a forward direction. So by angle bisector theorem, this is harmonic. So I can project onto like omega. I'll just call this circle omega. Yes, this one. So project onto omega. What do you get? N, oh no, not M. So like A goes to F, C goes to D. So that's FD. And X goes to M and what? X prime goes to N. So that is -1, right? Now, like what did you want? You wanted Mn to bisect AC. Now, I want to ask this because like this has been covered before, I think in config geo. It should have been because it's like the most basic config. So, yeah. Do you know about three tangents lemma? Like anybody? Or
Yeah.
okay, so you should know about it if you have done EGMO chapter 1 because like it was one of the lemmas in the exercise. So I think most of you know about it. Is there anybody who does not know? I'm talking about the three tangents lemma. Okay, somebody
Okay,
does
so
not know.
basically we want to show that XD is the tangent.
Yeah, true.
Yeah.
So, well, I'll just state three tangents lemma, by the way, for you. So, if you have a triangle ABC and you have the altitudes AD, BE, CF, okay, and also if you want a detailed proof of the three tangents lemma, I have like another lecture, Foundations of Geometric Thinking. You can check that out because like I just spent like 30 minutes on three tangents lemma. So that's a good resource, I guess. So yeah. So the like statement of three tangents lemma is if you have ADVECF as the altitudes and H is your orthocenter, then if you take the circle AFHE, then DE, DF, and the line through A parallel to BC are all tangent to
No,
this
no, it's the
circle.
midpoint of BC.
Sorry. Okay, shit. Okay, sorry. So this is if this is M, then ME. I was saying that why does it not look like that in the diagram? Okay, ME, MF, and like the line through A parallel to BC are all going to be tangent to this like circle, and that is actually a very easy proof because like you can just angle chase. Like you can take this angle. So this angle is equal to this angle because like ME is equal to MB because M is the center of the circle BFEC, right? And this angle is also equal to like this angle because BFEC is cyclic. So that just proves that ME is tangent, right? And MF is tangent in the same way, like symmetrically. And we don't even need that the line through A parallel to that thing is like tangent because we won't like need it anywhere. So yeah. Wait, what did you ask? what is the pole of AC in omega? Let me see. AC in omega. Okay, you can do like any spam. Okay, one sec. I'll just see it after you finish this problem. So yeah, this is a statement of three tangents lemma. So in essence, like if you think about its converse, then the tangents at E and F intersect at the midpoint of BC, right? So here, the tangents at D and F are also going to intersect it at the midpoint of AC. Is that clear to everybody?
Yeah.
Okay. And like while doing harmonic quadrilaterals, we just said that tangents at A and C intersect at BD and tangents at B and D intersect on AC. So like tangents at F and D here are going to intersect on NM, right? So R lies on NM. That is essentially the conclusion that you get. Yeah.
Yeah.
And R is the midpoint of AC. So NM bisects AC. Did that completely make sense? Is there anything that did not make sense here?
Yes, yes, it makes sense.
Okay. Uh, all right. Like, is everybody clear with all the problems we did? Feel free to ask me any questions. Anything I have to repeat or? And also, like, if this just looked very out of the blue for you guys, then like, why does this feel like cheating? I mean, what? Okay, fine. Like, what I was saying is that if this feels very out of the blue, then we are going to have a couple more of projective classes to like give you the entire picture. So just don't get intimidated by this because this is just a start of projective geometry and there's like a lot of stuff going on. So this is just some very basics and it might look like you can't solve any problems and any hard problems using this, but trust me, it's like the best tool for problems that look weird. So yeah, I think that should be enough for today's class. And I'll try to take another one as soon as I can. And yeah. So any of you have any questions to ask me?
Wait, what is the pole of that AC?
Okay. Can I think about it? Okay, I have to
I
think
think it is
about it.
DF cap BH. I'm not sure.
DF cap BH. Okay, wait. Pole of AC are you talking?
In omega, I'm pretty sure. Wait, I
Yeah, of
think
course,
yes,
right?
correct.
Of course, right? Because like BFHD is cyclic. So by Brocard, like if you take the intersection of BH and FD, and this point is like, let's call it to be S, then like SAC is self-polar, right?
Yeah, yeah. Wait, yeah, so yeah,
So
we can use
the S is like the pole of AC.
Oh, I thought we could just use I used like this problem when I did it, but okay.
Okay, all right. I get what you're trying to say. So to people who did not understand that, that's completely fine because we are going to do pole, polar, and Brocard in our next class. So it's completely
Wait,
fine.
can we solve this using pole polar?
I think we can, right? Wait. That's an okay. How about I stop the recording and like end the class
Sure,
and
sure.
then try to do it? Yeah, sure. Okay. So bye everyone. Hope you enjoyed the class and like feel free to DM me at any time and give me any feedback on the class. And I'll try to make a problem set and send you like as soon as I can. So bye.
Bye. Thank you.